Mitchell Peterson from Northwestern University is going to be talking to you today about panel data and how you can handle those standard errors in panel data. We're delighted to have him here. The FMA has started. This year is the kickoff with some econometric sessions. We will continue those for hopefully every upcoming FMA, where we will have a series of education for you in econometrics. And we are delighted to have Mitchell Peterson be the kickoff. So with that, I'm going to give the floor to Mitchell, and feel free to ask questions. And I'll try to moderate that, but do try as best you can to hold your questions to the end.
Yeah, if we want to do sort of clarifying stuff up during, because otherwise, if I confuse, you get lost, and bigger picture stuff at the end, I think.
All right.
Okay, thank you very much. I really appreciate Jacqueline and Ralph and Jeff Coles kind of put this together. And sort of it's unusual in the sense it's been published, but it's also unusual in different ways. We were a little worried about doing this right after lunch, because if you do something on econometric methods, given how boring I am, right after lunch, you'll put people to sleep. So I'm going to try to keep you awake for the next hour and a half. This is unusual in the second respect, in the sense that if you know anything in my work, not that you should, it tends to all be with real data. All the data in this paper, with the exception of the last two tables, are fictitious data. I made it up. Usually you don't get published stuff when you make up the data. This is an exception. I didn't actually mean to write this paper because I'm not an econometrician. So this will feel very different than other econometric papers. Frankly, I'm not smart enough to write those kinds of papers. This feels much more like a cookbook. And it basically comes from essentially two sources. Source number one is there are a bunch of junior faculty at Kellogg who would show up in my office under the illusion that I know anything about econometrics to say, Mitch, I'm estimating standard errors in a panel data set. What do I do? And I could easily tell them what I do, but then I couldn't really clearly articulate why my method opposed to all the other methods worked. And that always makes me uncomfortable. Other source of this was essentially a referee report, or a response to a referee report going bad. I had done one method, the referee had had a preference for another. And as I found it was difficult to articulate why I was right, and there wasn't any sources, I started to write a longer and longer response to the referee. 35 pages later, I clearly don't send to the referee, but I sort of had a first draft. So that's kind of what we're going to do. Now, if you hated Econometrics 101, you're going to have some bad flashbacks. And I'm going to do some simple stuff because I need to motivate. In some sense, the charm of this paper is its ex post obvious. The challenge of the paper in convincing anyone that you've learned anything is it's ex post obvious. If it's clear in explaining, duh, everybody's going to do it exactly this way. So let's start with some of the duh part. Estimated standard error. So when I think of panel data, the talk is going to essentially be I've got a bunch of firms and I've got a bunch of years. But in general, panels are you've got a bunch of observations within a unit. So I have firms within an industry, I have firms within a country. The reason I want to do the analog of firms and years is that's why it's not nested. And a lot of the actual data sets we look at are of that nature. We know that OLS works if and only if the residuals are correlated. And so I want to think about two sources in which they're not correlated, because that'll start helping us think about the way to solve it. Different methods work if you got the right data structure. And these are going to be the two major data structures. One is going to be the residuals are correlated over time. Meaning the 1980 observation for IBM is correlated with the 1981 observation for IBM. There's something unique about IBM. I'm going to call that a firm effect. If that's true, all the standard errors don't work. The other is a time effect. There's something about the IBM observation 1980 and the AT&T observation 1980, and those are correlated. And if that's true, that's a time effect. And OLS doesn't work. And everybody's nodding, so I know that I got this right. Now, if you go to the literature, you tend to see the methods that are used are correlated with the literature. Meaning, if you look at the asset pricing literature, they know the residuals are correlated, and they use Fahm-Macbeth both to estimate the coefficients as well as fix the standard errors. If I go to the corporate finance, this kind of depends if you're in corporate finance and you want to put a positive spin on it. Those are people who hate corporate finance empirical work, I don't think we know what we're doing, are going to put a different spin. I'm going to say we do something and we do clustering. Now, as long as there's historic reasons for that dichotomy, i.e. the data structures are fundamentally different, we're okay. And that's where I got in trouble with the referee. Because what's happened over the last decade is people that traditionally do asset pricing research have migrated to corporate, and some that have done corporate have migrated into asset pricing. And most humans, we bring our toolbox to the new environment, even if that new toolbox doesn't work. I thought this was a bias against corporate finance research. Because what would happen is I would write the paper, I would correct the standard errors using clustering, and I would send it off to the journal. And the referee would write back and go, no, clustering is all wrong. What you have to do is spam a Macbeth. And I figure, oh, that's just the asset pricing people thinking they're smarter than us corporate. So I was talking to my asset pricing colleagues and say, you know, I got the same problem. I write the paper, I correct the standard error to a file Macbeth, I send it off to the journal, and the referee writes back and goes, no, that's all wrong. What you got to do is clustering. So the new lesson is whatever you do, the referee will tell you it's the opposite. And that's kind of why we needed some framework for how to think about it. Now, the next thing in the sort of talk that I did, but like the last thing I did, is I went back to the survey. So when I got all the results I'm going to show you, it kind of dawned on me that they were ex post obvious. And I kind of realized I was probably the only one in the profession that didn't know this. Everybody else did. And to verify that, I thought I'd do a survey. You know surveys are sort of widely respected in finance, right? So I went and read 4 years of the Journal of Finance, the JFE, and the RFS. And I found every empirical paper that had a panel data set in it with at least 5 observations in each dimension. And then I went and read the tables and the footnotes and the notes to the table to figure out how they estimated the standard errors. This proves to be a lot more difficult than you might expect. It's not always clear. I had one table that sort of in the notes it said the standard error, robust standard errors are reported in parentheses. Now in many cases I couldn't figure out what exactly the author had done. And so I would email or call them. I discovered email worked better. If you call someone and say, I'm doing a paper on whether published papers have the correct econometric method, and I talk about yours, people are uncomfortable. So I tend to send emails. One of those people that had the robust standard errors in parentheses, I knew. So I figured I'm going to call him up and ask. And I said, you know, I noticed in your table 5 in your sort of 2003 paper, you report robust standard errors. Could you tell me what exactly that means? And there's a pause, and then they say, well, yeah, it means the standard errors are robust. Okay, no, I'm okay with that. But when you say robust to heteroscedasticity, robust to correlation, robust to what? And there's another uncomfortable pause. She says, I have no idea what you're talking about. All I did is in Stata, I typed regress, y, x, comma, robust. 42% of the papers that have panel data sets don't do anything. Meaning they report OLS or they report what? Which corrects for heteroscedasticity, but not the correlation. Now it could be that the authors did something else and they didn't tell us. If they did something else, even in a footnote I said I tried something else but I'm going to report OLS, that's not in the 42%. The concern is in the 42% there are the kinds of data structures you think OLS will not work. People are regressing leverage, which is a very persistent variable. On firm size or whether they pay dividends, a very persistent variable. That's exactly where OLS won't work. Or they're regressing bid-ask or earnings surprises against stock prices. Again, something that will have a time series. So there are an appreciable number that have these sort of kinds of data structures where you are worried. So that's why I thought maybe I was onto something I need to investigate. The rest lays out the methods, and it doesn't tell you a whole lot just looking at the surveys because it may depend on the methods. File Macbeth was the most common, and those tended to be priced or in asset pricing. The fixed effects and clustering were the next most common, and those tended but not always to be in corporate finance. Now, if you think back to some of your econometrics class, especially if you took a labor economist, things like the panel data techniques, so sort of the within estimate, the between estimates, the GLS estimates, you don't see that on the list. This is about 97–98% of the papers. So those last methods are about 2%. In econometrics and labor we've seen them, but in finance they've only recently started to bleed in. As I go through this talk, it's all about the standard error. So I'm going to assume the model is correctly specified. That's not because that's always the most important issue. It's just the issue I can talk about. I'm going to do the talk in 3 pieces. The first piece is I'm going to lay out some of the equations. And this is the part that's going to bother you if you hated Econometrics 101. But the equations let me do 2 things. One, they let me focus on intuitively what the big issues are. And 2, there's sort of a nice back-of-the-envelope calculation that gives you an order of magnitude. If I got to the end of this and I said, you know, your standard errors are wrong, they're off 4%, you would correctly say, who cares? So a back-of-the-envelope calculation will tell me they're off 4%, they're off 50%, they're off 400%. And by the time we get to 400%, that might actually matter. After I do that, I'm going to go to the simulations. And the simulations allow me to be more subtle in the explorations because I'm not good enough at algebra. And what I'm going to do is simulate a bunch of different data structures. And then every data structure, I'm going to estimate the standard errors in a whole lot of different ways. So essentially, I'm going to start to create a cookbook. If you want a chocolate cake, here's what you need. If you got firm effects, here are the standard errors that work. Now obviously, in something that's 40 pages and a talk that's no more than an hour, I can't hit every data structure you have. But I've got stated programs, because that's all I can program, that run the simulations, and up on my web page are the simulation programs, and to the extent I was capable, a program that does every method in the paper. So if you've got a data structure that's slightly different, you can go to my web page, download the simulation, put in your data structure, and essentially generate a small table 1 for your first dependent. And you refer to the paper and say, go ask Peterson all the details. The last thing I want to do is I want to come back to an application, because there's nothing in the simulations that really tells you whether this matters. And so the last two tables I want to show you, quote, an asset pricing example and, quote, a corporate finance example. And I want to do that for two reasons. One is sort of convince you that the magnitudes of this might be large. So these are the kinds of regressions that are effectively in published papers, and that's sort of the complaint I was worried about initially. The second thing it does is it starts to become a diagnostic technique. If you correct the standard errors and they change, that means there's something in the residuals that you're not accounting for. These methods don't perfectly tell you what that is, but to the extent they can give you some guidance on the economic nature of what you're missing, and you know the data better than anyone else, it'll start to give you a guide of what kinds of factors you might want to pursue. John Graham made the point that if you give someone a really hard technique, they're not going to do it. If you ask them to estimate standard errors with white, standard errors clustered by firm, that's easy. And if it's a simple diagnostic technique, we're much more likely to do it. It's also why I've got the web page. John Graham gets credit for that. Okay, equations. I'm going to essentially have a linear regression. All the variables are going to have mean 0 because it's going to make the math very easy. Your normal estimate for your beta, and therefore this is essentially going to be my formula for the variance. Everything interesting in the talk is going to happen here. That's sum of x epsilon across all years, across all firms, and then square the sum. And when we go to the next one, instead of the square of the sum, it's the sum of the squares. That's where we made the assumption. We've made the assumption the residuals are uncorrelated. And if you do that, boom, that OLS is going to drop out the bottom. Going from here to here is just an assumption of homoscedasticity. In the simulations, all the data is assumed to be homoscedastic. In the real data sets, the non-corrected standard error is white because I want to make sure that any variations in standard errors are coming from correlations, not from the heteroscedasticity. And in what we're talking about, the data sets, that's going to be the biggest effects. Okay, think about that sort of inside matrix. So there's an X matrix and there's an X prime. And the table I've got up here is that central epsilon, epsilon prime matrix. If you've got OLS, only the diagonals, and all of these have the same variance. If white's correct, you only have the diagonals, and these things have different variances. This is a case where there's a firm effect. And so those shaded off diagonals are IBM in year 1, IBM in year 2 is correlated. That's what's going to mess up the standard errors. If instead of a firm effect, i.e. these shaded were 0, you had a time effect, these things are going to start to turn on as being the non-zeros. The reason I want to put that up is it kind of tells you what we're trying to estimate. In the case where I've got 3 years, there's 3 off diagonals. In the case where I've got 4, now I've got, 7 off diagonals. So as this matrix gets bigger and bigger, you've got more off diagonals to estimate. It's going to turn out that's not a problem, because both the Fama-Macbeth done correctly and the clustering have a very clever way to do it. These asymptotics are going to be driven by essentially the number of clusters, the number of firms, or the number of clusters, the number of time. And I'll show you simulations where it doesn't matter, I have got enough to be asymptotically correct, and where I do matter. Because some of these estimates, these non-parametrics, the clustering, they've got small sample problems. And I'll show you at least one example. Okay, go back to that same expression. Here's the one we had before. If you let me pull the sum n out, that's assuming those off-diagonal blocks are 0. That's assuming no time effect. And then when I expand that term, I'm going to see the two pieces. This essentially is the white standard error, and this essentially is going to be that correction for clustering. In the simulations initially, and in all the equations, I'm going to assume the firm effect is constant, meaning the residual in year 1's correlation with the residual in year 2, and the residual in year 1's correlation with the residual in year 10 is exactly the same. Now that logic comes out of a labor analysis. in the sense your IQ in the first year and your IQ in the 10th don't tend to depreciate. Since corporate essentially stole the labor econometrics, we pull that assumption in. There's nothing in some of the analysis that requires it, but initially I'm going to show you with that. That means calculating these correlations is very easy, and it simplifies down to a piece. Now, here's where the intuition comes from. We know that if the residuals are uncorrelated, OLS white works perfectly. The contrary is not exactly right. Meaning, if the residuals are correlated, that doesn't mean the white clustered errors is a problem. You need the residuals to be correlated, you need the X's to be correlated, and you need more than one observation per firm. And that means it's this interaction that's going to drive it. And I'm going to show you in the simulations that you need both of them. The statement from my Econometrics 101 professor was correct. If the residuals are uncorrelated, white works. What I heard incorrectly is if the residuals are correlated, white doesn't work, and that's not exactly true. It also gives you a back-of-the-envelope calculation. If you have some intuition of what that rho x and rho epsilon is, you can sort of estimate this. And remember, this assumes it doesn't die off at all. If it does die off, it's going to be even smaller. In the case where it does die off, these things don't have to be positive. So if they're constant, they've got to be between 0 and 1. But if they die off, you can get situations where the rho x is positive, and at some maturities, the rho epsilon is negative. So in theory, when you do this clustering correction, the standard error could get bigger, they're both positive, or it could get smaller, the product is negative. One of the authors in the surveys that I knew, I called them because I noticed they'd done the whites, not the clustering. It was a young person whose econometrics I trust immensely, and so I said, I don't understand. Why did you do whites opposed to clustering? I said, well, actually, I did clustering, but the standard errors got smaller, so I figured there was a programming error, and I threw them away, and I reported the white. No, it's exactly the case where the standard errors go in the opposite direction. So there are situations where it drops. To think of an example, usually regulatory changes are the best. You got a dummy variable before the change for 5 years that's 0. You got a dummy variable that's 1 for the 5 years afterwards. And so when you start looking at that correlation across there, you're going to get a negative. If your other x's are persistent in the epsilon, I haven't found a lot of examples, but I found a few. Okay, so that's where I'm going to head. With the simulation, what I'm going to do is I'm going to simulate a data set of about 5,000 observations. 500 firm, 10 years. I'll change this and I'll show you where it matters. Usually it doesn't. I'll have an x and an epsilon. By definition, they're going to be independent. This is not going to be analysis of model design. Therefore, I'm going to have a y. And then I'll run an OLS regression, and I'll save the beta. I'll save the standard error for OLS, and the Fama-Macbeth standard error, and the cluster standard error. I've got 4 variables. I've got 1 observation. And then I'll do it a second, and a third, and a 5,000th time. And when I'm done, I've got 5,000 betas. If you take the average, it's going to be 1 because the model's correctly specified. If you take the standard deviation of those 5,000 slopes, that's the true standard error. Think about what you mean when you say my standard error is x. You're saying if I had not one data set, but a lot of data sets, and I ran this regression a whole lot of times, how much variability will there be in the beta? Well, I actually get to do that. I actually get to see it. So the standard deviation of the beta is the true standard error. I'll take the average OLS standard error and see if it's the same as the standard deviation of the betas. If so, it works. I'll take the average Fama-Macbeth standard error and see if it's equal to the standard deviation of the Fama-Macbeth betas. If so, it works. In almost all cases, I'll show you these averages. Now, there are a couple of cases where the averages are misleading, and I'll give you some intuition where that might pipe up, and also intuition why most of the time it doesn't. The last part I need for the simulation is I need to fill these in. And originally, I'm going to do it with a firm effect that's constant and a residual that's uncorrelated. And then I'm going to do it with a time effect that's constant and a residual that's uncorrelated. And then I'm going to put both in, and then I'm also going to add to that residual a slowly declining correlation. And that's going to give me not a permanent firm effect, but a temporary firm effect. It'll change the magnitude, and for some of the standard error methods, it's really important whether you got a constant or a temporary firm effect. I'll do that in the x and I'll do that in the epsilon. That took me about 3 days to figure out. The first 3 days of the simulation, I had the epsilons correlated and the x's were uncorrelated. And the OLS standard errors were beautiful. They were absolutely perfect. And I spent 3 days debugging the program before I realized the program's right and my intuition is wrong. If you think I'm smart and I know all this stuff, it took me years to figure this out. And I was the dumbest guy in the room when I started. So if it takes you a couple of days, you're a hell of a lot faster than I am. Okay, simulations. I'm going to have the correlation of the independent variables at row x go from 0 to 75% in 25% increments. Those are the columns. I'm going to have the correlation row epsilon go from 0 to 75% in 25% increments. Those are the rows. Up here, there's no correlation to the epsilon. There's no correlation to the x's. The beta is 1 on average. This number is uninteresting as a check in my programming ability. This is the standard deviation of the betas. This is true. This is the average OLS standard error. That's the estimate. And so I want to see the third number is close to the second. Across the top row, they line up perfectly. When residuals are uncorrelated, OLS works. Along the first column, they work perfectly. Even if the residual has a 75% correlation, you can crank this up to 99%. It doesn't change. The fact that x's are uncorrelated means you don't need to correct the standard errors. The number in brackets is the fraction of t-statistics that are statistically significant at the 1% level. It's the fraction of t-statistics that are bigger than 2.56. We may not care just about the average standard error. We may care about the confidence interval or the t-stats. And so that's why I'm going to report it. In almost all cases, what you learn from the t-stats and what you learn from the average standard error will be exactly the same. Third thing, go down the diagonals. And as you go down the diagonals, you'll notice that the estimated OLS standard error does not change. Well, that's because it's a function of the variance of x, the variance of epsilon, and sample size. But that second number blows up. Instead of 286, it's now up to 698. That's because the more correlation you have when you go from 1 to 10 observations, the data says you don't really have 10 more observations, and I'm going to hurt you by giving you a high standard error. The number of t-stats that are statistically significant at the 1% level, 29%. In terms of publication efficiency, that bottom right corner is really great. Now that was meant in humor.
Yeah.
When I gave this at BC, Phil Strong was furious at me. He said there's a bunch of PhDs in the audience and they don't know when you're telling the truth and when you're trying to be funny. They actually think that's a goal. No, that's the problem. It's going to be hard to publish those as people figure this out. The last thing to look at the table is this fifth number is the average clustered standard error. And when I say clustered, I now have to become more precise. Clustered by firm. Because what I realize is you can cluster in lots of dimensions. And doing the wrong dimension isn't going to help. If you have a firm effect and cluster by firm, this is the part that's ex post obvious, it works. Not only the standard error is correct on average, but the t-stats are coming in at 1%, so that works perfect. Not terribly surprising. If something else was going on, I'd worry. Okay, some people like the picture better. So what I did is the blue bars are the distribution empirically of the t-stats, and then the line's what's supposed to happen. In the case of the cluster standard errors, 1% or 0.9% of the t-stats are statistically significant to 1%, and the critical value is about 2.6. If you let rho x and rho epsilon get up to 0.5, which isn't huge for a corporate data set, you now find that about 15% of the t-stats are statistically significant to 1% level. And the critical value is not only 2.5, it's now up to 4.6. Now think about magnitude. See, that's why I want to do this. If I've got 10 observations, if the rho x and rho epsilon are 0.5, and you tell me your t-stats 3 uncorrected, that's going to be a problem. There's a labor economist at Dartmouth who says, Mitch, you really need to simplify it. It's too hard. I would cut the paper down. I would keep the abstract and this figure. I think that's all you need. If you want a short answer, 30 seconds on the seminar, that's it. Okay. Here's where I want to get back to the number of off-diagonals you have to estimate. So as you go from 5, 10, 50 years for the sample, you notice that the red triangles go up. This is the fraction of t-statistics that are statistically significant at the 1% level. So it should be 1. By the time you get up to 50 years, you're getting 70% of these things statistically significant. Again, jokingly, good for publication, terrible if you're interested in truth. Notice the cluster standard errors doesn't move. As you get more and more off-diagonals to estimate, you don't tend to lose anything as you need more and more years. And the reason is what clustering is going to do, think back to that equation, it's going to take a sum for each year of all those off-diagonals. And the method doesn't care whether that sum is based on 1 number, or 2 numbers, or 6,000 numbers. So essentially, the asymptotics are how many observations you have on that cluster, and 500 firms, how many observations you have within the cluster is completely irrelevant. And that means that what you're going to worry about when you cluster by firm is not a lot of firms, not how many years you have. This is the purpose of this figure. Okay, let's go to Fowler Macbeth, because that was the other one that I was dealing with. So every time I simulated a data set, I did an OS standard error, a standard error with clustering, estimated the coefficient by Von-Macbeth, and the standard error by Von-Macbeth. Since I've got 10 years, I did 10 cross-sectional regressions, and I took the average of the 10 slopes. That's the beta, the top line. And again, it's consistent because the model is correctly specified. More importantly, if you look at the estimate for Von-Macbeth in Table 2 and the estimate for Von-Macbeth in Table 1, and you do the correlation between the slope coefficients, in every cell the correlation is at least 0.99. Meaning when the model is correctly specified, they're effectively giving you the same information. They get to it in different ways, but they give you the same information. Buried in there, for someone smarter, I'll bet there's a specification test, because I think it's weighting the data differently, but in my example, weighting doesn't matter because the model is correctly specified. If you then calculate the standard deviation of those 10 observations, that's the standard error. This is the Von-Macbeth estimate of the standard error, this is the truth. And this structure looks exactly like Table 1. The first row, Von-Macbeth standard errors work perfectly. Zero correlation to residual. The first column, Von-Macbeth standard errors work perfectly. Zero correlation to residual. If you go down the diagonal, that's where these two things start to diverge. And now, notice we've got not the 25, but we're up to 50% of these t-stats are statistically significant at the 1% level. So in terms of sort of getting the wrong answer, this works a lot better. Sorry, at this point I get confused which way it is. Now, to see it, let me go back to the equation. And I'm going to show you that in some sense this is obvious. These things are ex post obvious. And the reason I wrote the paper, the reason I sort of made the effort, is in the journals that's not always obvious. Because people hadn't thought about it. I don't think it's they don't get it when they think about it. The minute they think about it, they get it. It's just we haven't thought about it. So, Von-Macbeth, you add up the 10 observations, divide by 10, so this is the variance. Part of that's going to depend on the variability of the coefficients divided by 10. That's the estimate that is normally used for Von-Macbeth. In the literature, there's a new version I'm going to talk about in a little bit, but most are the standard deviation divided by 10. But you know, if the IBM's observation in 80 is correlated with the IBM observation in 81, then the slope from 80 has got to be correlated with the slope in 81. And that's what this second term is going to pick up. If those correlations don't die away, it makes calculating that covariance very simple, and boom, you've got that estimate at the bottom. Now notice that expression at the bottom you've seen before. It is literally identical to the standard error for the OLS if you get it wrong, the truth. Means that Von-Macbeth will be biased in the same kinds of situations as OLS, and numerically the equation says exactly the same. The residuals are correlated, Von-Macbeth doesn't work. If the x's are correlated as well, Von-Macbeth doesn't work. Well, let's look at the figures. 1% is statistically significant, 15% is statistically significant. Up here, we're up to 25. In terms of a critical value, 2.5, 4.6, 6.7. So now these numbers are getting enormous. So you tell me you've got a 6 t-stat, nobody's going to question, and I'm going to tell you that's actually not a 1%. Now, the disturbing part is if I go back to the previous one, that equation is identical. But then when I show you the pictures, Von-Macbeth isn't giving you exactly the same distribution. It should, but it's actually got a lot more out here in the tails relative to this. Something's wrong. Go back to the table and look at what's going on. So across the top row and column, I get it. But as you go down the diagonal, the estimated OLS standard errors do not change. The true standard errors go up. The estimated Von-Macbeth standard errors do change, and instead of getting bigger, they're getting smaller. That's why the two distributions look different. Now, to see this, this is where I've got to use Jeff Cole's RA. So what Jeff did is he told his RA, who will remain nameless, to go out and pull 20 years of CompuStat data and go run this regression for Jeff. And the RA was relatively new at this, so they pulled the same year 20 times. And that means they ran the regression for 1980 and got a Von-Macbeth slope. They ran the regression for the next year, which is 1980, and got a slope that's exactly the same. And they've got 20 Von-Macbeth slopes, and when they take the standard deviation of those 20 identical numbers, it's 0. Because there's no uncertainty. You've nailed it. See, what happens is when the correlation rho x and rho epsilon go up, the first year isn't very different than the second year. So there's actually two sources of bias in the Von-Macbeth. One is the correlation, and that affects the white, the OLS, and the Von-Macbeth standard errors. You'll notice the Von-Macbeth standard errors are worse here than the OLS standard errors. They both rise as you get more years, because now you've got more dependence, but that gap shrinks. The gap is coming from misestimating the variance. See, if you've only got 1 year, you're estimating that year relative not the true mean, but the sample mean. And if you've only got 5 observations, your sample mean isn't very close to your true mean. If you got 50 years, your sample mean moves into your true mean, and therefore that variance piece goes away. They're going to be exactly the same for large years. They're going to be even worse for small years. Okay. I've gone through this, and I kind of warned you because I didn't want to get shot down, but some of this stuff is ex post obvious. This also helps you understand the refereeing process. This is the only paper I've ever been able to include in the talk quotes from my referee reports. So I want you to be in the mind of the editor who gets a paper excitingly titled Estimating Standard Errors in Panel Data Sets in Finance. Now, the kind of paper like that, pick a referee. You go to an econometrician, because only an econometrician would be able to judge whether these standard error estimates are right. An applied person like me, you would never ask. And what does that econometrician tell us? I would be surprised if researchers are systematically applying the wrong methods at the top of the answer. Or the one that I thought was really positive, I said to Mom, a sophisticated applied finance researcher knows everything that is in this paper. Well, I'm clearly not a sophisticated applied finance researcher. That part's clear. That's when I had to go back and do the survey. Because I thought, maybe everybody knows this. And see, the problem is there's a set of econometricians who develop estimates but don't deal with data, and none of the estimates I'm going to tell you, you haven't learned. Depending on how recently you've been in grad school, you saw in your PhD class. For me, it's been too long. None of the methods are new. The question is whether you use the method. And the problem is in the finance literature, we've got papers written for econometrics that here's the method. We don't really have cookbook-type papers that says, here's how you use the method. Occasionally somebody writes an applied paper and there's an appendix that shows you how to do it. This is a cookbook. I want to sort of figure out how to do it. Okay, so now you're sitting there in your Peterson, you're trying to figure out how to respond to this referee report. One suggestion was go back to your survey, go back to the 200 papers and ask the people for the data set. Say, I'm going to test whether your published papers got the right standard errors. Could you send me your data set so I could check? Now, Betty, since this isn't being taped, I'm sure there will be no sample selection in the data sets I receive back. So I did something else. I said, I'm going to go and pick some genres in the literature and kind of see if there's genres where I think there might be a problem. And then at the end, I'm going to go empirically test it. So I picked 3 genres. One, and all these are corporate finance because that's what I know best. One is whether a firm pays a dividend. So the left-hand side variable is a 0-1 on whether a firm pays a dividend. Now think about predicting whether they pay a dividend next year as a function of today. Today's a pretty darn good guess. It's essentially not a correlation 1, but high. We're going to regress on leverage, which happens to be incredibly persistent, and firm size, which happens to be incredibly persistent. And I picked a random paper that was doing this, and they're essentially using what I'm going to now call Fama-Macbeth, but the naive Fama-Macbeth. Actually, I think there's no relationship between this one and the previous Fama-Macbeth. Okay, version 2, valuation, market to book. So I'm going to regress market to book, which has a lot of persistence, against firm's age, whether they pay a dividend, leverage, and firm size. Now, these 2 papers do something different. They're going to essentially, one is going to use Fama-Macbeth. Pastor and Veronese is going to use what I'm going to call an adjusted Fama-Macbeth. So they very clearly understand the intuition I'm driving at, that naive Fama-Macbeth ignores that covariance, and they're going to step in and fix it. What's interesting in their paper is they say when we go and correct for that correlation, it has no effect on the Fama-Macbeth standard errors. Now that part seems really weird, in the sense of here's a case where you have persistent variables. It's clear that ordinary Fama-Macbeth is biased. It seems like the adjusted should work, yet it doesn't move it. So I'm going to come back to the adjusted Fama-Macbeth and sort of talk about that method. The third version, this is sort of the market I play in, is the capital structure regression, and you're used to the usual suspects. Johnson uses normal Fama-Macbeth. Baker and Wergler actually report white standard errors. But in a footnote, they say we actually went back and estimated the standard errors using Fama-Macbeth, so they're in the Fama-Macbeth bucket, but it didn't matter. The Fama-Macbeth standard errors are the same as the white standard errors. That's, I'm sure, true, and therefore the standard errors are correct. No, 2 answers being the same doesn't always mean it's correct. In fact, I showed you if the sample size T is big enough, your OLS, white, and your Fama-Macbeth standard errors are going to be really wrong and sit right on top of each other. There's another paper by Fama and French that uses a slightly different method. We use a less formal approach. We assume the standard errors on the average slope should be inflated by a factor of 2.5. So you take the von Macbeth and you multiply by 2.5 to get it bigger. Now, it's actually more serious than that. They're essentially doing the adjusted von Macbeth, and that 2.5 is going to come from that, and I'll show you where it comes from. I was presenting this at a place on the south side of Chicago. And there was an individual sitting here who had a lot of sort of capital in this sort of field. And didn't say anything for the whole seminar until I got to this slide. And he didn't say anything, but there's a young individual in the back who I think is very high IQ, but politically doesn't always read the situation. And he says, they inflated by factor 2.5. Where did 2.5 come from? Which is exactly my question, but fortunately I had an expert. So I said, do you have an idea of where the 2.5 comes from? And to Gene's credit, he's an incredible scholar and phenomenal with numbers. And I had this table up, and he goes, yeah, Mitchell, go to the third column, go to our fourth column, third row. This cell, I like that cell. It's off by 2.6. So I mean, Gene's doing this in his head. Now, he's doing something more subtle, but there is going to be a data structure where that works. And the question is, does that subtlety, does that adjusted von Macbeth work? And the answer, like everything in the paper, is if you got the right data structure, it's beautiful. You got the wrong data structure, it doesn't work so much. Okay, we teach in the literature by example. So as senior and junior and PhDs, we want to know what the methods are, we go read the literature. And if people are using von Macbeth or OLS or White in the capital structure literature, we learn that's what you should do. It's actually worse than that. Not only do we lead by example, but we tell people what to do. The von Macbeth method is used to account for the lack of independence because of multiple yearly observations per company. Just not right. The von Macbeth regressions take into account cross-correlation, serocorrelation in the error term, so the t-statistics are much more conservative. It does account for the cross-correlation. It doesn't for the serocorrelation. They're not more conservative. And I want to be very careful to stand up here and say I'm really smart. Once I figured this out, I am. But before, I easily could have been one of these people. And remember, some smart person wrote it. Some smart referee signed off on it. Some smart editor said it was okay. That's why I figured somebody's got to get out there and say, here's the method. There's also a political dimension here. One of the people I talked to that was using the von Macbeth method said, I don't understand why you use it. And he said, Mitchell, I'm untenured. I come up for tenure in a couple of years. And the referee, when I did clustering, said I have to use von Macbeth. Do I use the right method and not get the paper published? Or do I do what the referee said and get the paper published? What's your call? Well, they can't take the political heat. Somebody else has to. But if there's a paper out there that's published that says, actually, this is where the method works, go see whoever, that's the purpose of this. It also works on the referee side. You know, if you get a paper that's using the wrong method, how much of your time, honestly, are you willing to invest in doing an education for that author? It is asking an awful lot for you to sort of give them a tutorial on econometrics. If you can say, go read Peterson and do it, and there are a couple of people in the room who I know the referee said that to you, because I got emails from you saying, the referee said, go see your paper, and I have your code. That's a home run. Then I figured I actually accomplished something. Okay. Where are we on time? I think I'm in good shape. Okay. I'm okay? Am I talking too fast? I talk really slow and I put people to sleep.
It's fine.
Yeah. I'm paying. Okay, time effect. So I showed you what happens if IBM and 80 is correlated with IBM and 81. Now I want to show you what happens if IBM and 80 is correlated with AT&T and 80. And what I'm going to do is cheat a little bit. In the sense, I'm going to cluster by time. So when there's a firm effect, I cluster by firm. When there's a time effect, I cluster by time. When I get to the von Macbeth, I'm not going to let them be that flexible. So it's going to look worse for von Macbeth, and I want to come back to why that's a little bit unfair. If you look across the first rows, White standard errors, OLS standard errors do perfectly, so does the clustering. If you look down the columns, OLS White does perfectly, and so does the clustering. If you go down the diagonal, well, notice how far the true standard error is from the OLS estimate. Now we're up to about 88% of our t-stats are statistically significant. Rho X and Rho epsilon are the same as they were in Table 1, but instead of having 10 years per firm, t-1 is 9, I've got 500 firms per year. The analog of t-1 is 499. So across different literatures, depending on the dimension, this thing can be astronomically a problem. The clustering does much better in the sense, notice 49, 40, but this isn't 1%. This isn't 0.49. And this is the Achilles heel of the clustering. For clustering to work, it's a non-parametric technique. So if you think about those off diagonals, there is no assumption about what the structure of that correlation is. other than it's the same across the different firms. That means the asymptotic comes from the number of clustering. And based on table 1, 500 firms, 500 clusters is enough. Based on table 3, 10 years, 10 clusters is not quite enough, and somewhere in between is. And so what I did is just sort of go back in the paper and I drew some pictures, and it looks like 20 is getting close, 40 seems to be there, 50 is clearly there. That's also why I posted my code up on the web, because if you've got some odd data structure, you can go do the simulations and kind of figure out how bad is that small sample bias. The strength of the clustering is there's not a parametric assumption. The weakness of the clustering is it's only going to work if you have enough clusters. But that's true of all non-parametric techniques. Von Macbeth is beautiful. Von Macbeth was designed for the time effect. And so even when it's 75-75, it's nailing the standard errors perfectly. Here's a case where Von Macbeth does better than clustering, because that small sample problem I talked about clustering, for reasons I have not figured out, doesn't affect Von Macbeth. So that means there's cases where you want to use Von Macbeth, you don't want to cluster, even if you've got the right dimension. Now, go back to the history of the literature. If you go back and read the Von Macbeth paper, remember it's published in 1974. So think about the notebook computers that they were using in 1974. One way to think about Von Macbeth is Gene, and I don't know Professor Macbeth's first name, was an absolute computational genius. Because you couldn't computationally do clustering. I don't think it had actually been developed. But had it been developed, I don't think you had the computing power. How do you calculate a standard error correcting for it? You run 10 simple regressions, you take the standard deviation, it's brilliant. Now, if you go read the paper, after they talk about their standard errors, there's 2 sentences I've read 20 times and I never understood. After running the regression, we looked at the serial correlation of the residuals. It is 0, period. They understood this in 1974. They understood it only worked if the residuals were uncorrelated. But what happened is later generations like me came along and it doesn't say why checking that standard deviation serial correlation matters. Well, it matters because Von Macbeth won't work if it's not 0, only works if it is. They knew it, the rest of us read it, and we didn't fully appreciate it, which is how we got into this situation. Okay, I've done firms, I've done years. And that's where the historic artifact comes from, because in corporate finance, you tend to have firm effects. Those firm characteristics are persistent. In a lot of the asset pricing, you tend to have time effects. Something happened in, I don't know, August of 2007, for example. It's really nice to be able to talk to a finance audience for an hour and a half and not mention financial meltdown. What I want to do is, what happens if you have both? So if you go back to the literature and you look at what people do when there's a firm effect and a time effect, there's essentially 2 approaches. Approach 1, the one I've used, is you parametrically account for one dimension and we would put in time dummies. And then we non-parametrically account for the other dimension, we'd cluster by firm. And parametrically solving this works perfectly if you nail the parametric structure. And it doesn't work if you don't nail the parametric structure. And I will show you that. Doing it non-parametrically, that's hard. In fact, in the first 3 versions of the paper, it said it is impossible. You cannot cluster by 2 dimensions. And then I got a paper by a guy named Sam Thompson at Harvard who said, actually, you can. And again, it's one of those things that's brilliant and obvious after you point it out. But nobody in labor figured it out, nobody in finance, and thanks to Sam, I think the finance people are going to be ahead of the labor this time. He said if you cluster by firm, you pick up all those off-diagonals I need for firms. If you cluster by time, you pick up all those off-diagonals I need by time. The problem is you picked up the diagonals twice, so you need to go back out and subtract off one of those diagonals. This picks up a firm effect, this picks up a time effect, this means it adds up correctly. If this works, this is incredibly clever. Given the time, I'm going to show you one picture and no table. There's 4 things here, or 4 kinds of estimates. There's an OLS estimate, clustered only by firm, clustered only by time, and clustered by both. The firm effect is about 1/3 of the variation, because I want a big firm effect. The time effect is about 1/3 of the variation, because I want a big time effect. And what I do is I have 10,000 observations. 10 firms, 1,000 time periods. Or 1,000 firms, 10 time periods. Because I want to know how number of firms relative to number of time periods drives this, holding the sample size, holding the rho x and rho epsilon constant. Well, if you've got few firms but enormous amount of time, clustering by firm doesn't buy you a lot because you've only got 10 firms. Clustering only by time buys you immense amount. Clustering by time and firm, and remember there is a firm effect, buys you nothing. That's that small sample problem. When you've only got 10 firms, there's a bias. So when you look at the firm and both, you know that there's a time effect. When you look at the time in both, you either know there's no time effect or no firm effect, no firm effect, or the small sample hurts you. Now, if you had 10 firms, the second's a possibility. You got 100 firms, the second isn't. In the case where there's a small number of firms, it doesn't help you. And here's where my comment about 40, 50, 100. Notice when you get to 40, 50, and 100, you're down to 1%, and so that clustering in both dimensions work. If you got about 40 firms, if you got about 40 time periods, this seems to be a back-of-the-envelope potential. Okay, everything I've done so far has been basically a firm or time effect that doesn't die away over time. And that comes essentially from the labor logic. The problem is, in finance, we've now got longer and longer time series. If you had 6 years of data on a firm, you could say fundamentally the firm hasn't changed. Same CEO, same industrial structure, same production process. You get to 20, 30, 40 years, well, the CEO's probably changed, the industry is morphed, the production process may have changed, it's now exporting to China. It doesn't work. So what I want to do is I want to go back and say, if those effects die away over time, they're a temporary firm effect, does it change any of the conclusions we have? And the short answer is it changes the magnitudes, but not the qualitative intuition. And then I wanted to look at a couple other estimates that I have not talked about before, and I saved them here because the different data structures, permanent or temporary, give you different answers. On the Fomig Bev, on the clustering, not so much. Okay, the permanent one is that correlation is going to be constant. The temporary one, I'm going to have two things. I'm going to have a permanent component that doesn't die away, and that last residual, the eta IT, I'm going to assume is an AR1. So if the permanent effect doesn't exist, and you only have the AR, it dies away pretty quickly. If you don't have the AR and you have the permanent effect, you're back to my first four tables. I'm going to look at situations that are mixed where it dies away, but it doesn't die away completely. Okay, here's an example where the permanent effect's 0.5 and the temporary is 0. Here's a construction white standard errors works. When I had this first result, I went back up to the Stata FAQs because it said, do you need to cluster standard errors if you use the routine that puts in firm dummies? And the answer was no, or no you don't, they're perfect substitutes. That's exactly the case. If you put in the firm dummies, clustering buys you nothing, doesn't hurt you. If you don't, you need the firm dummies. Only in this column. See, if you go to the second column, where that effect dies away over time, you put in the firm dummies, it takes out part of the firm effect, but by definition, since I was assuming the correlation was constant, and the real one died away over time, it didn't take it all out. Since some was left in the residuals, your OLS standard errors are still biased, although less so, and you still need to cluster. Oh good, I know something the Stata FAQ doesn't. I whipped up to the page because I wanted to send one of those I know something emails, and they had edited the FAQs. They're actually not substitutes. Someone else had also figured out that it only works in that polar case. Okay, here's what I mean by a diagnostic. Do you have a firm effect? Well, one way you're going to do that is you're going to put in firm dummies. Did that solve the problem? Well, do the OLS standard errors, do the cluster standard errors, and if they turn out, or actually do white and do cluster by firm, if they turn out to be the same, then your firm dummies sucked out the entire firm effect. If you put in the firm dummies and you look at the white standard errors and the cluster standard errors, and they're still appreciably different, it hasn't pulled the whole thing out. In my regressions, there's only one independent variable. In most of our regressions, there's multiple independent variables. So there's a row epsilon that's the same across all the variables, but there's a whole bunch of different row x's. And so this answer may give you one for the first variable, but something different for the second. So not only does it tell you there's some firm effect left in the residual, but it'll also tell you which independent variable you need to focus on. That's why I think John was very clever in saying this can become a diagnostic technique if you start to look at it. The other ones are just giving you orders of magnitude. This one also always sets off bells for the referee. In every other column, she had the same row X and the same row epsilon. That last one used different ones. Why? I went and did a capital structure regression. And so essentially the row X's and the phi X and epsilons are designed to replicate the one AR process of the epsilon and the X and the 10th order AR1. So that last column kind of looks like a capital structure simulation in the sense I'm going to use the same data structure to the extent I can guess and put it in there. And that's just for orders of magnitude of seeing which of these matters. And again, this number is big. Okay, I've got two more sets of results and I'll show you the empirical ones. Briefly, this is the fancy panel data that none of us tend to do. See, in panel data sets, we either do a sort of pool cross-section time series or we put in a bunch of firm dummies. But if the standard errors are different, if the firm dummies matter, then there's information in the residuals you're not accounting for. So what you really should do is somehow create a more efficient estimate. Well, that's what GLS does. And if you compare the standard errors in this table, 513, to the standard errors in this table, 284, that reduction is that greater efficiency. I picked up the information, the residuals, I didn't eat up 499 degrees of freedom in doing it. So that's sort of the nice part. Again, this assumes it's correctly done. Does it work? Well, if you do GLS, your normal Y standard error is perfect, clustering buys you nothing. If you do GLS, your normal Y standard error isn't as good as the clustering. Notice it works in the same column where the firm dummies work, and it fails in the same column where the firm dummies fail. Why is that? Well, that GLS is a weighted average of two estimates. One of those estimates is the firm dummies, that within. So essentially, once you put those firm dummies in, it controls it. The between is a regression of the average for IBM at Y on the average for IBM X. One observation per firm. Well, if there's only one observation per firm, the residuals aren't correlated. So none of the problem comes from here, it all comes from here. And if the firm dummies perfectly take it out, the Y standard errors are beautiful. If the firm dummies do not perfectly take it out, the Y standard errors don't. So even when you do GLS, you still need to do the white versus the clustered to see if it's different. See, when you do GLS, you're implicitly assuming those firm effects are permanent. No one tells you that because it comes from the literature, but that's the implicit assumption. Third and last technique that I'm going to talk about is the adjusted von-Macbeth. Now go back to the expression for von-Macbeth. There's a variance term and there's a covariance term. And when Jeff's RA went and collected 20 years of data that was highly correlated, the problem is the betas were the same. You need to account for that correlation. Well, if that's true, all you should have to do is estimate the autocorrelation of the betas and do a correction. And if it's infinite order, this is the correction. Some of these papers do a finite period correction. I'm only going to do the infinite because I'm looking for direction and order of magnitude. But you see, it's a growing literature. And this should work perfectly, which is why when you go back to the Pastor and Veronese paper and they say we did the regular von-Macbeth, we did the adjusted von-Macbeth, which is smart, exactly what they should do, and the answers are the same, that's the part I don't understand. And that's why I want to go look at this. Okay. What I did is I've got a permanent effect and there's no temporary effect. I estimate 10 betas, and then I calculate the autocorrelation of those 10 betas. And remember, since rho x and rho epsilon are really big 0.5, those betas are going to be highly correlated. What's the first order autocorrelation of those betas that are highly correlated is minus 0.12. It's minus? No, it can't be. It's got to be positive. If you do the adjusted von-Macbeth, the 239 is wrong, is too low. When you correct it, it gets even smaller. The number of t-stats are statistically significant, doesn't shrink, it gets bigger. It doesn't help, in fact, it goes the wrong direction. That's a small sample problem. I've only got 9 or 10 years. I've only got 9 observations to estimate that autocorrelation. If you move it up to 20 years, minus 0.12 becomes minus 0.06. If you move it up to 30 to 40 to 50 years, that first order autocorrelation converges towards 0. In an environment, we know it has to be positive. Go back to Jeff's RA. He's got 20 years of data. He estimates 20 slope coefficients that are exactly the same. What is the autocorrelation? 0 variance, 0 correlation. See, what's happening is when you estimate that autocorrelation, it is the observation the first year minus the sample mean, times the observation the second year minus the sample mean. And this firm effect moves up that first year slope a little bit. It moves up the second year slope a little bit. It moves up the 10th year slope a little bit. It moves up the mean by the same amount. So the thing that's causing the problem is going to be differenced out. And just as you increase the number of years, the variance problem goes away. As you increase the number of years, the time period goes away. If the effect dies off, now we get a positive autocorrelation and it improves, but this is not down to 1. This is not back up to 0.66. Here's where one of the referees was unbelievably helpful. They kept giving me suggestions that were very clearly correct, which I hadn't thought of, but they're also brilliant. They never said, "You're an idiot, Mitchell." They said, "It seems to me that what you're doing," and then effectively it was a very nice way of saying, "You're an idiot." But I was, they're right. So he said, "It seems to me that if the autocorrelation fell off fast enough and you had enough years, the adjustment would work." Exactly. So let me show you 2 versions. Here's a situation where the correlation doesn't die off, And as you get more years, this is exactly the table I showed you before. The dotted blue is the correction. Well, if the effect doesn't die off, that autocorrelation is negative when you have 5 observations. It's negative and smaller when you have 10, and it converges to 0. Here's aspirin Veronese. I did the naive von Macbeth. I did the adjusted von Macbeth. To the extent the firm effect is highly persistent, I'm not going to see it. The referee is the red. Notice, if you do the adjusted von Macbeth, even though it's an error of about 0.9, once I get up to 50 years, that thing decays. It's not down to 1%, but it's down to 7%. So they're absolutely right. The adjustment will not work if you don't have a lot of data and it's very persistent. The adjustment will work beautifully if it dies off quickly and you have lots of data. Then I kick it back to you to ask you, sir, what your data set is. Okay, 2 more tables, then I stop. Everything I've shown you is made up data. The next 2 tables are real data. So this is a paper by my former colleague Kent Daniels and Sheridan Tippman. Kent went on visit for a little while, so I broke into his office and borrowed his data set. That tape may get me in trouble. The returns are monthly returns. The independent variables are annual values. So I'm going to have the January 80, February 80, December 80 returns, but I'm going to have the 1980 variable. And I'm essentially going to run regressions of book to market 10 years or 5 years ago, how the book values change, how the market value, market returns change, and their measurement of share issuance. Now I'm not going to talk about the economics, I'm talking about the values. What I want to do is go estimate this data set using white, cluster by firm, cluster by time, cluster by book. And that's going to tell me whether it's a firm or time effect, and then I'm going to do the von Macbeth. Now, if you notice, white has got to be the baseline because there's heteroscedasticity here. So these differences only correlation. If you look at the difference between column 1 and column 2, not much is going on. That's the firm effect. Well, if you think that returns in an efficient market are somewhat unpredictable, if you look at the autocorrelation of the epsilon, it's essentially 0. There is no firm effect in the residual. You don't need to cluster by firm. If you cluster by time, 426, 1440. 257, 1000. These standard errors are going up by a factor of 3 or 4. The magnitude on this is huge. Oh, I've also already got time dummies in. So do time dummies and white standard errors. And the time dummies suck out all that time effect. Do time dummies and cluster by time. Having already got the time dummies in, standard errors go up by 3 or 4 times. Now what's going on? This is essentially that same table 5. The dummies, the parametric work perfectly if it exactly sucks out the functional form. If the time effect is in January 80, there's a shock, and IBM goes up by an extra %, and GM goes up by an extra %, and Kraft goes up by an extra %, time dummies take it out, clustering does nothing. But let's say August of 2007, or better yet, September of 2008 is a really bad market, and the non-durables fall a lot, 10%, and the durables fall an enormous amount, 30%. Well, now when you look at that correlation, GM's residuals really closely correlated to Chrysler's, and Bank of America is really closely correlated to JP Morgan, but they're not terribly correlated to Kraft. So to the extent you have a systematic factor, the market, but you've got firm-specific exposures, the beta. Notice you don't see beta times the market. Whenever you've got firm-specific exposures to an aggregate risk, the time dummies will not take it out unless all the betas are the same. But clustering will tell you it's there. So based on this, I know there's some factor, the market, with firm-specific exposures, betas, I just don't know what it is. And since this isn't my literature, I'll kick it back to Kent to go figure it out. Now, this assumes the model is correctly specified, so at a minimum, you might want to know what that factor is because it could be interesting, you get more efficient estimates. At a maximum, it also may be correlated with the residual, and you kind of want to go figure it out and check it. This is a capital structure regression. Actually, let me quickly go back. If you cluster by time and firm time, you now get nothing. Well, that means either there's no firm effect, or to a small sample bias, I can't pick up the firm effect. They've got 1,000 to 3,000 firms, there's no small sample bias. There's no firm effect. So I compare column 1, column 2, column 3 to column 4, and know I've got lots of firms, there's no firm effect. There is a time effect. Von Macbeth does very well. It's not quite the same, although I don't know why. In the simulations it should. That's why I wonder if there's some issue with the model specification. In real data there always is. Okay, now the capital structure. Here the answer is what we expected. If you cluster by firm, the standard errors go up by a factor of 3 to 4. Clustering by time gives you very little. Clustering by both is essentially clustering by firm. Found Macbeth essentially looks like doing white. Well, this is my point. In those papers that have very persistent firm effects on the left side and the right side, the white isn't going to give you the right answer. The found Macbeth isn't going to give you the right answer. You got to cluster. Okay, what's the ex post obvious answers? You do the correct method, you get the correct standard errors. You do the incorrect method, you get the wrong standard errors. I figure if I make fun of myself before you make fun of me, it makes it a lot easier. The whole purpose of the paper and the presentation, this is her idea, was giving you a roadmap. So as I said, the way I view the paper is when you've got a situation, you go to the paper and you try to figure out what data structure you have, and hopefully it's a cookbook enough that says, here's the method. It also gives you some intellectual background and some political cover, i.e. shorter response to referee, here's the answer. Hopefully it will make programming a lot easier if you can, quote, steal my code. You don't program in Stata, my apologies. I barely program in Stata. If you write the stuff in other languages, let me know. There's code up there in SAS and a couple of other languages, which I did not write, but I will link to. So I'm happy that if you put it up on your website, I will link to it, which again is a great service to the profession. The biases I found surprisingly large in published papers, and back to John's point, I think this is a diagnostic technique, is very cool. Go to that table 6 or go to that table 7 and say, what firm effect or time effect is there, and do I miss it? And by doing white, cluster by firm, cluster by time, both. Add the firm dummies or the time dummies. Cluster by firm, cluster by time, cluster by both. We're up to 8 or 9 regressions. That's not a whole lot, but man, you all of a sudden have an enormous amount of information about what you've accounted for and what you haven't. And I think that's all I've got to say.
So thank you, Mitchell.
Thanks very much, Jacqueline. And, well, we won't be nearly as good as Mitch Peterson.
You can just kind of leave it.
Actually, I'll be as good as Jeff. All right, so what do I want? Jeff and I have been sort of working on this for a long time. Actually, I think we started back in 2001. And trying to bring a little bit more structure to some corporate finance research, and also try to just understand ourselves how problematic the endogeneity problem is, and what we might do to fix it, and also what more can we learn. And so that's going to be sort of our talk. Let me give you the caveats up front, right, is that we will base this talk on what we know best, which is our own work. We do rely on the work of many others prior to us. The economists especially have been using sort of calibratable models for a long time, and corporate finance seems to have lagged behind in this area. And we're starting to see, I think, finally, this sort of approach gain some traction in the literature, and we'll point to a few of those papers at the end. So, what are our objectives? First, to try to provide a clear, I hope, statement of an important difficulty that we face as empirical corporate finance researchers. Second, to illustrate how actually I think you can write down a fairly simple parsimonious structural model based on some fairly well-accepted economic principles that provides some gauge of how organizational form and different corporate governance aspects might interact within the firm. And then finally, to wrap up by illustrating some of the methodological benefits of such an approach. In particular, right, one is it helps give some insight into the black box of the firm, because we're able to sort of quantify the various economic effects of different parameters, and Jeff will point out some of that. And finally, right, we may or may not have the right model, but within the model that we'll present today, everything is an endogenous value maximizing decision, and so we know that everything is endogenously determined, and we can test within that framework how well some of the standard econometric remedies actually work, and we can understand why they might fail in the real data. Okay, and so we'll spend some time there. And then finally, what I think is perhaps the most useful part of writing down a structural model is you can then start to be very serious about policy analysis, right? Because structural model, we can say if you change this exogenous variable, if we implement a regulation that says everybody should have an independent board, what will that do to the other governance mechanisms? What will that do to firm value? And we will have an illustration. The SOX board reforms present just such an experiment that we can apply to our model. So that's where we'll be headed. So quick outline. Right, what I'm going to start with is a couple of examples that I think illustrate the challenges we face as corporate finance researchers. And I'm going to use two sort of well-known areas of the literature to illustrate this, stock returns around equity issues and capital structure stuff. Okay? Jeff's going to then talk about what we call secretly the coffee problem right now. Jeff will let you know what that is. And then talk about governance and organization design. Then we'll provide sort of a taxonomy of empirical experiments in corporate finance, and we're going to focus on two specific canonical models, mainly the relationship between Tobin's Q, or firm performance, and managerial pay for performance sensitivity. And then we'll look at the interaction between managerial ownership and board structure within the framework of our model. Okay? So that's what we have. All right, so let me talk about a couple of examples that will set the stage for why I think it's important for us to start to take a deeper look at things. Right, stock returns around seasoned equity issues. Our traditional view of this sort of topic, right, goes back to Myers and Mazliff. With asymmetric information, an equity issue conveys bad news to the market. Who wants to issue? Managers who know their stock is currently overvalued. Well, the market, of course, understands this, and when they see an issue, they know the firm is overvalued, they adjust the price accordingly, right? And the manager can't benefit from the overvaluation. More importantly, right, if the market's efficient, that price adjustment is permanent, and there's no future abnormal returns following the issue. Well, then we started looking at the stylized facts, right? And Lawford and Ritter and various others, right? And what are the stylized facts? Well, first of all, there's a large run-up prior to the issue. And Lawford and Ritter document 93% stock price run-up in the year prior to issues for SEOs, right? Then there's a -2 to -3% price drop at the announcement. This is the well-known announcement effect. And then more recently, right, people started looking at the longer run performance and found post-issue underperformance for 3 to 5 years following the issues. This is from Lawford and Ritter. SEO firms return 7% per year on average. The matching firms 15% on average. And of course, it's highly statistically significant, that difference. So approximately, right, 7% per year underperformance for SEO issues. Right? And so we started rethinking the traditional view of how to interpret this evidence, right? This doesn't quite look like what Myers and Mazliff sort of told us. And so the new view, right, sort of became a quasi-behavioral theory of returns around issues. Investors become over-optimistic about some firms and push the values up away from fundamentals. Managers realize this and take advantage of these quote-unquote windows of opportunity to issue overvalued equity. More important, right, the market reacts only partially at the announcement. Instead of the Myers and Mazliff price drop and then nothing, right, the market doesn't understand how overvalued the firm was. They only adjust down partially, and then we see this long-run post-issue underperformance. Right? So that became, I think, sort of a fairly accepted view. Well, recently, some people have been sort of re-examining this view within the context of more structured models about what we should really expect in an efficient market. And I'm going to basically use Carlson, Fisher, and Giammarino's JF paper as an example. Right? What do? They write down a real options model of the firm. The firm consists of assets in place and an option to expand. And there's two types of firms in the economy, good and bad. Looks a lot like Myers and Mazliff's original setup, right? Investors will revise their beliefs over time about the value of the growth option. And then the key insight they had was, right, the growth option is a levered position in the underlying assets of the firm. When the firms invest to exercise the growth option, the leverage falls, which means the equity beta falls, and we observe relative to a matched firm that has not yet exercised its growth option what appears to be long-run underperformance, right? Well, how successful is this model at replicating the stylized facts? They calibrate this model to the data and simulate what you would see around SEO in a perfectly efficient pricing framework. What do you see? 93% run-ups, 3% stock price drop at the announcement, and long-run post-issue underperformance that basically replicates not only in sign but in magnitude what has been observed empirically. Okay? Well, so we have two theories now for the same set of observed facts. How can we actually differentiate between these two theories, right? And, what's not clear is what the two theories would say about risk differences and the risk dynamics around equity issues. So what Carlson, Fisher, and Giammarino do, right, is try to look at where the two theories might have differing implications. And in particular, right, I think this is a good picture from their paper, is the behavioral story, right? The run-up is overreaction to good news, and then slow realization of the valuation error in the post-issue period. The real options theory, it's a rational reaction to good news, and lower risk and lower returns in the post-issue period. Okay? Well, this is what the beta dynamics actually look like around SEOs. Here are the SEO firms, and here are the matched firms. And indeed, it looks a lot more like what the real options model would predict. Betas are going up prior to the issue, and then betas fall dramatically post-issue. So perhaps what we've been observing in the data is not so inconsistent with what one would expect in a typical neoclassical world. Okay? So that's example one. Example two, capital structure, another well-researched area in finance. And we have sort of the traditional theories again, the trade-off theory, perhaps the best known, and the one that we all teach to most of our students. Right? Firms trade off the tax benefits of debt and maybe the benefits in controlling agency costs against the financial distress and the other agency costs generated by debt. What's the main implication of this theory, right? That the firms have some kind of target capital structure. Then there's the pecking order theory, right, which is just the hierarchy induced by information asymmetry, internal funds first, debt second, and equity only as a last resort, right? Well, then, right, again, more recently, people started documenting stylized facts, and we started to invent some new theories based on those stylized facts that didn't seem to fit the traditional view. And the two most well-known, right, are Baker and Wordler's market timing story. Managers issue overvalued equity, but the second part of their story, right, which you have to have for it to affect capital structure, is managers don't rebalance away the effects of those overvalued equity issues. Right? They don't later realize that, hey, there's a bunch of tax benefits being left on the table. Maybe we should actually lever up now that we're no longer overvalued. So you need that second part. And then Ivo Welch's 2004 JPE paper, right, where he says that inertia may not be exactly the best word, but he finds that although there's lots of security issues, they don't seem to be done in a way that appears to counterbalance the effect of shocks to the firm's equity value. So if your returns go up a lot, your leverage falls, right, trade-off theory says you ought to be re-levering back upward. And I'm going to use Ivo's paper to sort of illustrate the issue. And what does he do? He forms two variables. He forms the actual debt ratio at time t, and he forms what's called the implied debt ratio. And all the implied debt ratio is the actual debt ratio at time t with the equity value inflated by the stock returns between t and t plus k. So this is the shock to the equity value of the firm, right? And then you estimate a regression of the future debt ratio, t plus k periods in the future, on the time t actual debt ratio and this implied debt ratio. And then there's two hypotheses, right? The perfect readjustment hypothesis says you should readjust these equity shocks to get back to your target debt ratio. So alpha 1 should be 1 and alpha 2 should be 0. there's the total non-adjustment hypothesis, which predicts just the opposite. Right? Everything should be on the implied debt ratio. And what's the basic result in the paper? If you estimate that regression, what you find is everything loads on the implied debt ratio and nothing loads on the actual debt ratio. It looks like the perfect non-adjustment hypothesis, right? It looks like firms are not adjusting. And so that's the conclusion. Well, again, what if we take a slightly richer view of the standard trade-off theory and add adjustment costs? And there's good empirical evidence, right, that it is costly to issue securities. And there's even evidence that those issuance costs are fixed and weakly convex, right? And if you take a Fisher, Heinkel, and Zechner type of model, a dynamic model of capital structure with adjustment costs, the way that adjustment should look is your leverage ratio, you'll let it wander around with changes in the value of the firm, i.e. the shocks to equity, until you hit some boundary. And then with fixed and weakly convex cost of adjustment, you don't adjust all the way back to your target, you only adjust back to some intermediate level, right? Well, you can immediately see from this picture, right? First of all, equity returns will have a big effect on your observed leverage, and moreover, you can be away from your quote-unquote target leverage for quite some time, right? You can find times when you're away for a long time, okay? Well, what if we took this model, simulate data, again, right here, firms are making completely optimal decisions about capital structure. We simulate data from this model, and we estimate the types of regressions that Evo does in his paper. That just duplicates the results from Evo's paper. This is the regressions run on the simulated data. And I don't know about you, but they look awfully similar, right? You can basically, again, replicate the observed stylized facts with a standard model, or a fairly standard model, of optimizing capital structure behavior, okay? And so this particular empirical test really has very little power to discriminate between these two views of the world is essentially the message, okay? So to me, right, I sort of use these two examples to illustrate just how difficult it is to construct powerful tests that allow us to discriminate between different stories for the same observed phenomenon, right? And I think that you can think of lots of other examples where we face these same problems, right? And sometimes it's competing traditional theories, sometimes it's competing behavioral theories for the same phenomenon, sometimes it's a traditional theory versus a behavioral theory, right? I'm not arguing that any of these particular theories is correct or incorrect. I'm not trying to take a stand that the world is, you know, the neoclassical world, but that our empirical tests are very weak oftentimes at being able to discriminate among these views. Okay? All right, so a couple of things, right, to bear in mind as we go forward, right, is if we want to make progress, we have to actually think of what the null hypothesis we're testing against really is, right? Is it behavioral versus nothing, or is it behavioral versus a dynamic trade-off theory, right, with adjustment costs? Focus on where the predictions of the competing theories differ, i.e. the Carlson-Fisher-Giammarino look at the beta dynamics as an alternative prediction rather than just the return predictions, right? And then try to construct powerful tests, right? And some of the questions that I think you should be asking yourself when you're thinking about doing tests in empirical corporate finance, right? How good does measurement have to be in order to discriminate between these hypotheses? What I've found is that doing some simple simulations often can give you a lot of guidance on what kind of tests you might be able to run and you might be able to use. And, you know, for example, the simulation I just showed you of the dynamic trade-off theory is a good example. Right? We're seeing a huge sort of surge in papers using natural experiments to get around the endogeneity problem. Natural experiments are great, except that one, they're rare, and two, they're hard to generalize. And I think that this current wave is going to run its course fairly quickly. What Jeff and I are going to focus on, right, is structural models and trying to bring more structure to the way that we do empirical corporate finance. Okay?
Thanks, Mike. Or maybe I I should call you Mitchell. Thanks for coming today. I'll have to tell you, it's a little strange having a camera pointing at you up front here, because really you sort of feel like you have to play it straight. And I can see in Mike sort of the cracks appearing in the concentration that he had in doing that. But I'm going to say some of the things that Mike said by way of introduction, but I'm going to say them a little differently. And not that, I love the way Mike thinks about it, and my approaches tend to be a little more rudimentary, but I just want to do that to set ideas and fix ideas. And to start, instead of the coffee problem first, I thought I'd actually talk about a taxonomy of evidence, how we think about generating evidence in empirical corporate finance, for example. And the methods that I'm not going to be talking about, just to be clear, event studies, we all know what event studies are, and then analysis of decisions where you look to see whether good or bad decisions have to be correlated or related somehow to some characteristic or aspect of organization form. So we're not going to look at those. What I'll be paying closer attention to are regression models of performance and structure. And in some cases, performance as a function of organization structure. So we'll call that performance on structure. And other cases where you take two aspects or characteristics of an organization and see how they're related in choices that vary across firms. So I'll call this structure on structure and performance on structure. Just as part of the taxonomy, and this is a core dump here. I'm not going to talk about all of this, but I just wanted to provide some idea of what I mean by structure. And here's a laundry list, and you probably have even a longer laundry list of this. And but organizational choices include capital structure, like Mike has suggested, dividend policy, whether or not you have anti-takeover devices in place, what you do with your corporate charter. Are you a U or an M-form organization? Where are you domiciled, et cetera, et cetera. I've got in red a couple of aspects that you will pay close attention to shortly. Ownership structure or maybe compensation policy for executives. So we'll be thinking about effective pay performance sensitivity that arises from all possible sources: salary and bonus, stock ownership, options, et cetera, et cetera. So how aligned are managerial interests with shareholder interests? And then we'll think maybe a little bit about characteristics of the board of directors. And here's a long list, and I know you can add more items here. But we'll think particularly about independence and monitoring and advisory role of the board of directors in the structural model that we generate. Okay, but here's choice variables that are structured, and then there's a whole list of things that you might think of as performance measures of performance. We'll be thinking about a whole set of experiments in the literature on Q, where Q is the performance measure. But you could accounting returns, market returns, various valuation ratios, market value, et cetera, et cetera. And then, of course, in all of this, there might actually be some things that are exogenous or predetermined you might want to control for. I mean, nothing's really predetermined, right? But some things are relatively predetermined. So here are some things you might want to control for when you're regressing, say, performance on structure or structure on structure. State law, nature of the market for corporate control, what's happening with monetary policy. We'll be thinking about technology and the production process and how various factors of production affect cash flow. So that's what we'd be thinking about. But there are all sorts of other things that are swimming around here that you might, depending on the nature of the experiment, want to control for. Okay, so there's this literature, and I've sort of sliced up the literature into pieces, and the outcomes, what do we really know from performance P-on-S experiments and S-on-S experiments? Well, I think we've got a wide array, as Mike illustrated, of suggestive empirical observations, and these are typically drawn, I'd say, from very reduced form sorts of specifications. So that's one good thing, I guess. Another good thing is that policymakers and academics, investors are all sensitized to what we think of as organization design and the general public thinks about as corporate governance. And so these things are seen to be important, and actually maybe some of these audiences are too sensitized to the issues. And I don't want to scold anybody or say, hey, gee, nobody knew about this. I think we all know about, and we all worry about, issues and causation issues that underlie the performance on structure and structure on structure experiments that we're so used to generating in our industry. You know, I've certainly, I'll cop to quite a few mistakes. I think Mitchell Peterson, well, he was making fun of me this morning over something else that we did with data. But you know, I've certainly made my own set of mistakes on this too. And I think we all worry about spurious results from misspecified empirical designs. We didn't control for the right thing. Maybe we've got wrong functional forms, et cetera, et cetera. So you know, solutions, people are putting good effort and they're trying very hard at this, and we'll assess whether or not this is a practical way to go. But very often people will attempt econometric fixes with fixed effects, control variables, try to construct various instruments, try to do simultaneous equations, and that's all good. But I've got to circle back every time and ask the question that I think maybe we really care about. From all of this, what do we really know about the structure, the nature of the firm, and the economic forces that determine organization form, and the mechanisms that are chosen? How do they really solve a problem? How do they really solve a problem? So that's kind of where we are, and I'm going to tell the same story in the context of what I call the coffee problem, and this is great. Medical doctors, you know, they're always designing experiments. This leads to that, or vice versa. And medical doctors, well, they're not actually real doctors. They're medical doctors, right? You guys are all real doctors, PhDs. Some of that medical doctor stuff. And so correspondingly, they're not all that good at experimental design, whereas we all are. Right? But the experiment that was very influential was a correlation between coffee and outcomes, unfortunate outcomes for pregnant women. And so the idea that the finding, lots of coffee, drink lots of coffee per day, lots of cups per day, and you're more likely to have birth defects, premature labor, low birth weights, et cetera, et cetera. So the policy physicians were saying, cut back on coffee, and let's educate the public on coffee. All right. Well, I'm very pro coffee, so I like this example. The omitted cause of both was, as it turns out, smoking. They forgot to control for smoking, which, I mean, maybe that seems like something you ought to control for. So the idea is that, hey, people will go out and I'm not going to say I love smoking, but maybe I would. But lengthen the number of work breaks for smoking, that might actually lead to more cups of coffee, right? And lots of smoking might actually be associated with additional unfortunate outcomes in pregnancy. So the idea is that here's something that's exogenous, or sort of relatively exogenous. I don't know, maybe because you're pregnant you want to go smoke. I'm not going to speculate too much. But anyway, so here's something that maybe sort of relatively predetermined that drives both of these things together. And so if there's a connection, an observed empirical connection, and it's a strong one, maybe it's spurious. Now, it may still be true. It may still be true that there is a connection between these two things, and that coffee actually has an additional effect if you were to isolate the smoking part. Okay, so that could be true, but if you're forgetting about smoking, then even if there is a relationship, you'll have a biased estimate of the strength of that relationship. So it could be spurious. If there is a relation, your estimates are going to be biased. And oh, by the way, and this was the last comment I made on the previous slide, I think really the question for medical doctors and real doctors is what kind of structural model of physiology and biology captures the nature of the causal mechanisms from smoking or from coffee to unfortunate birth outcomes. You know, so in this soup should go gene structures and all of the other things we know about physiology. But that's the kind of thing that we're trying to do with organization design in firms, I think. We're trying to figure out some of those things. This is inside, this is the biological black box, and we're interested in the organization design black box, the black box of the firm. Okay, so at any rate, that's how I want to set ideas on this, and I think the coffee problem, if we can just call it the coffee problem to make it easy, I think that's very, very common, and I'm going to illustrate our approach to the coffee problem a little bit and trying to get inside the black box with some work that we've been going on. I don't know exactly when we started this, maybe even in the 1990s, but we're slow workers. I mean, Mike, of course, is a perfect co-author, but I think I've slowed this down a little bit. And I fell into that. At any rate, so we'll talk a little bit about some work Mike and I have with Felix Meschke and Albert Wang. And the intention here is to develop an application of a structural model. So we're going to develop and apply a structural model to governance questions. And I'm hoping that we can illustrate why it's important to do so. One is to get inside the black box, and the other thing is we'll be able to understand whether or not econometric remedies or fixes for endogeneity and causation can be effective. And then I think this is really cool, and I hate to say it, but it was Mike's idea, using these models, these structural models for policy analysis. Okay, if you're picking an empirical laboratory, right, to work on these issues, and why not pick one where there's 100 papers published and another 50 working papers? So that's where we started. And this is the Regress Q on managerial ownership literature. So we have this hump shape, McConnell surveys. Now Mark Slifer and Vishnu got something a little more edgy or jagged than Marcus Zorro or something. Sort of the Z shape. McConnell surveys have this inverted U or hump shape relation, and a lot of papers have been written on this. And again, the big question here in red is, well, what are the economic forces that would give rise to that hump shape relation between Q and ownership? Well, one possibility is that there are really big transactions costs of adjusting managerial ownership. And so the transactions costs are so big that you have an interval within which the data traces out the objective function, actually the thing that you would maximize with organization form choice managerial ownership in the absence of those transactions costs. So if transactions costs are out here and out here, if you're inside on this objective function, it ain't worth it. It isn't worth it for you to move from here to here by adjusting organization form, or from here to here. And so, if the transactions costs are big enough, and you prefer this, you may prefer this kind of argument, they're big enough, then what you will be tracing out with the data and estimating in the data is the form of the objective function. So a la Stoltz, for example, down here you'd like to bump up managerial ownership because you align incentives better, but you can't because it's too expensive. And out here, well, you overshot, and managers have too much ownership, and by golly, they've got too much power and they're entrenched, and you'd like to move them this way, but the transactions costs of doing so are too large. So that's one possibility. Now, if you're telling that kind of story, I think you've got to say, well, here's why the transactions costs are big, and actually take a crack at how big they've got to be to prevent moving from suboptimal to optimal. So in some data we've got, if you move one standard deviation, you increase on average value by about $700 million, which seems kind of big relative to the plausible transactions cost. So maybe that's not a great story for the Q on managerial ownership story relation. So another possibility is that firms actually are optimizing. Direct transactions costs are low. They have these humps, and everybody's picking the top of one. And basically, the tops of these things, what you observe in the data, this hump is an envelope of those maxima. So in this case, what that means is that there's something else, like how much smoke can you do, that determines where your hump, your objective function is, and everybody then goes away and maximize. Maybe they have different protection technologies or something. Go away and maximize, and the hump that you observe in the data traces all these maxima. And so this is the kind of optimizing model I think that we're very used to and familiar with if you don't want to work in a world where you have transactions costs, or you don't believe transactions costs are big enough. Am I being clear? Is this okay? All right, so that's performance on structure, and so we have basically pay performance sensitivity or managerial ownership. We're also interested in board independence, and but there's plenty of literature on Q and board independence. Some authors, here's where after when they find a positive relation, other ones find no relation, others find a negative relation, and not that that's disconcerting, that depending on data and sample periods and firms, that we find different answers all the time, but well, maybe it is disconcerting. So this is not particularly well settled, but this is another performance on structure experiment that we're going to embed in our model. Finally, you think about pay performance sensitivity and board independence, and you know, should we say we've got a really great board, and you know, it's really truly suitably independent, and it's the great board. Does that mean necessarily that we ought to have more pay performance sensitivity? Well, maybe, maybe not, but certainly a lot of people in the when they're working in the literature think about these two as being substitute incentive alignment mechanisms, and so we think maybe that we ought to be finding a negative relation between pay performance sensitivity or managerial ownership and board independence. And you know, certainly that's compelling logic. Of course, it would be nice to have a production function that helped us understand this, but that's compelling logic. But the empirical evidence on this, again, is mixed. And so how are we going to try to do something more incisive and figure out what's really going on? All right. Well, here's one attempt at it, and this is not the greatest model. There, you know, this is just one attempt, and I know people are working in parallel fashion on other models. This is just meant to illustrate the ideas that we've got about the issues. So in this model, we've got a standard agency problem, or a hidden effort, or hidden action by the manager. Think of it as effort or managerial input. And there's a firm scale decision: what's inside the firm and what's outside the firm. And then we've got a board of directors, and the board plays two roles. Outside directors have a comparative advantage in monitoring. Okay? On the other hand, inside directors have a comparative advantage in industry-specific expertise that makes CEO input more productive. Okay, so we're going to have a tension between insiders and outsiders on the board of directors. Very, very basic. And we are going to specify a structural model of the firm where the two inputs are basically assets and managerial input and monitoring or inside expertise. Right? Those are the obverse of each other. So the productivity of physical assets is denoted by Y, managerial input, Z, and outside director monitoring or advising by T. And this is all in a Cobb-Douglas framework that I'll show you in just a second. And those are the exogenous things. Remember, the things that are relatively predetermined. You can argue that technology is going to change, and you might actually try to affect technological change, but we're going to fix those for now. And outcomes, optimal choices in the model are pay performance sensitivity, basically the slope of the compensation scheme, firm size, we'll call that I, and the proportion of outside directors, independence of the board, M. So here we are, Y, Z, and T are going to determine these things. And oh, by the way, we'll calculate a valuation ratio, Q, our best mathematical attempt to represent what Q would be on the cost spectrum. So how much value is created relative to assets and points. So what we're going to do, though, is kind of solve the model and revert the model. We are going to allow these inputs that we don't know, these structural parameters, these production parameters, to vary across firms so as to match observed values of board independence, firm size, and managerial ownership. So we're going to assume that we're going to back out the model Y, Z, and T that you would have to make what you observe on contract form, firm size, and independence be optimal. Okay, so we're going to invert the model or solve the model and go back and extract those productivity parameters, trying to get at something primitive that's in the production function. And so this is kind of the standard aggregation and linearity approach. We'll have an additional investment decision. We are reflecting a comparative advantage versus inside versus outside directors. And here's all of the choice variables again: firm scale, board independence, and ownership share or pay performance sensitivity. So here's the cash flow, and this looks very Cobb-Douglasy, right? Cash flow is equal to monitoring to the power T, physical assets to the power Y, and then 1 minus M, insider representation times G, which is managerial effort, all to the power Z. So insider representation enhances the effectiveness of CEO input, and on the other hand, outside directors are going to help us, and so physical assets, you bundle all this with physical assets, and then there's a margin parameter out in front, P, that reflects units in the Cobb-Douglas sense, and also margin in the industry, except for managerial compensation, which we're going to take out in a minute. And then there's a little bit of risk, and we don't exactly know how risk increases in firm size. So we have an I to the X, and we don't know what X is. Well, we do because we estimate it in a minute. But then we have two disturbance terms. One is idiosyncratic firm risk, and this could be technology shocks, and the other represents another form of cash flow volatility that is distributed with a second moment that is the square of 1 minus m. Okay, so if m goes to 1, this goes to 0 because board monitoring. Okay, so that's where board monitoring comes in. So more outsiders implies lower cash flow volatility through this avenue. Okay, but it is clear, looking at the functional form, that expected cash flow is not always an increasing function of outsider proportions, right? Because insiders, remember, insiders, firm-specific knowledge can affect the productivity of the CEO. Okay. Am I forgetting anything, Mike?
Not that I know of.
All right. Manager's expected utility, is a kind of standard functional form. Where we have risk aversion and the expectation and adjustment for risk and adjustment for effort. We're assuming a linear contract in the Holmstrom-Milgram framework, and you maximize expected utility with a functional form like this. You have manager's optimal effort here, which depends predictably on a bunch of stuff. It depends positively on firm scale, on the margin. Oh, by the way, on the slope of the contract, probably bigger slope of the contract, you're going to have more effort. And then it depends, well, we don't know exactly how it depends on monitoring because there are two things in there. And the objective then is going to be to maximize total expected surplus. Here's the expected cash flow. You subtract out what you pay the manager, what you invested initially, and then you account for risk preferences of the manager in that second term. So there are individual rationality constraints. You've got to make it worth their while to participate. Here's a participation constraint. Oh, and by the way, has to be worthwhile to actually run the firm. So that's the other constraint. And then the other constraint, of course, is the manager's incentive compatibility constraint. You actually have to understand, you can understand and know what their effort choice is, even though you don't actually observe it. Okay? So it's kind of a standard model. First order conditions, there they are, and of course we'll check second order conditions. But if you have these equations, this describes how these inputs would give rise to these outcomes as optimal choices. Symmetrically, if the thing is invertible or solvable, these outcomes would tell you what productivity parameters would have had to have been to generate these outcomes as optimal. Okay, so that's kind of the way we're going to go. And these solutions, these equations here, represent that, where each of the three optimizing choices depends on those three productivity parameters. Oh, then an X, I'm going to have to tell you where that comes from. Then risk aversion, volatility of one of the idiosyncratic disturbance terms, and margin. And then here's our best, and this is really a simple model, right? This is a one-period model, unfortunately. Okay, so we're trying to represent, well, Q, which really is a present discounted value of some stuff, divided by assets, and this is our one period representation. There's the surplus, which took out I, and so we add back initial investment, and then there's the disturbance term that noises us up, and then here's initial investment. So here's our one period representation of Q. Really simple. If we get any traction with this, what the heck, maybe we're really lucky. Here's data. I think everybody in this room is going to know these data sources, so I'd like to pass on. But if you want to look at this more closely, take a look at the slides. Are these slides going to be posted? Okay. So in our data, just a couple of things. Ownership, mean and median, 0.03 and 0.01 here on effective ownership, and as I said, we're bundling ownership and effective ownership arising through options into this calculation. So that's basically delta, slope of the contract. And then in the sample, we've got mean and median in terms of outside directors of about 3/4, just to give you a sense for these data. And then we have percentiles here. I'm going to take a look. Okay, let's talk a little bit about sort of the calibration and the estimation procedure. So there's a bunch of stuff that's exogenous here, and so we've got three things that we're observing. So we either need to do some sort of method of moment or some sort of standard estimation technique, or we try to reduce the dimensionality of the inversion problem. We've got three things we observe. We reduce the dimensionality of the parameter space maybe to 3. So that's essentially what we do. We pick risk aversion per Halbrich's JPE paper, and that's 4. We actually estimate sigma, the idiosyncratic cash flow risk term, from data, and we got 0.33. So that's coming from somewhere else. That's we put that in, and the way in which cash flow risk scales up in the firm, when we estimate this in the cross section, the X coefficient, the X is about 0.5. So we are let's see, I always get this mixed up. Are we linear and standard deviation? No, linear variance and square root and standard deviation. Okay, so that's how it goes. So risk goes up, cash flow risk goes up as the firm gets bigger, but in the square root sort of way. So and then we have a profit margin P out in front, except for managerial compensation, which we take out already. And we are calibrating that at the industry level. So we guess at that, we go and estimate Z, Y, and T for each firm, and then we go back and see if we can do better with P to match the first and second moments of Q in each industry. And eventually we converge to Z's, Y's, and T's, those productivity parameters. They give rise to contract form, firm size, and monitoring or board independence. Okay, so that's a quick and dirty description of it. And the parameters here, we have on average a Y that's about 0.5. Think about Cobb-Douglas production functions. Let's do a reality check. Then we have a Z that's about 0.024, and this is the managerial input. I don't know if that looks right to you or not. That's what we get on average. And then here's the monitoring, the average monitoring coefficient there, about 0.00248. In our data, we have 2.26 on the modeled Q, so that's not all that different from Qs that we calculate on CompuStat, the median about 1.85. And here's a sense for the range of our modeled Q. Okay, so we have this model, and we've estimated things that flow through the model, these structural parameters, these production parameters, that should explain, we think, should explain variation of things you observe, like contract form, like firm scale, and like board independence. And then we'll get to Q also. So does the model generate things that seem sensible to us? Here's kind of a first check of this. So for example, if Y goes up, the productivity of physical assets goes up. Well, fortunately, investment goes up. We think it ought to. And ownership maybe goes down. Well, I don't know about that. Our intuition on ownership going down is that